Welcome to the session on SD-WAN terminology. I'm Ali, a technical leader in enterprise networking. And today with me on the panel is TLOCs, a senior software architect in advanced services. Hi, TLOCs.
Hey, how are you?
Doing well. How are you?
Yeah, doing fine. Good to be here.
And joining us also is Zain, a technical marketing engineer. How are you doing?
Thanks for having me.
Good to have you. This session will explore the terminologies that are used in the Cisco SD-WAN solution. Presenting for us today is Vinay Prabhu, a technical leader in SD-WAN engineering. Hi, Vinay.
Hey, Ali. Thanks for the introduction, and I'll quickly move on to what we're going to cover today. So how we're going to go about it is actually look at how the SD-WAN solution comes alive, and then deep dive into the terms that we use specifically for our solution, which may or may not be industry standards, but which will be used often. You'll be hearing about it in daily speak when we're talking about the SD-WAN architecture. So just a quick recap. We have the edge devices. These could be sitting at the branch offices, the data centers, the campus. We have the controllers, which could again be on-prem or sitting in the cloud. We have the NMS software that sits in the cloud as well. And then we have one additional piece, the orchestrator, the vBond, which basically stitches everything together for you. So let's go on to the terminology itself. So what we're going to cover today is we're going to double click on the edge, the vSmart, the vBond, and the NMS. So let's go down to the different components. So you have the vEdge. This could be software or hardware. We have the vSmart. This is only software. We have the vBond, again a software component. And we have the vManage, a software component as well. Let's start with the vEdge itself. So the vEdge could reside at different sites. I'll elaborate more on this. So each site is essentially a branch office or a data center, an endpoint where you want to actually direct your traffic to. These sites, for redundancy, could consist of multiple vEdges that we'll call nodes. So this is providing physical redundancy for a particular site. For each of these nodes, we'd have further redundancy in terms of circuits, and each of these circuits are identified by something called TLOCs, what we call transport locations. On the vSmart end, it's pretty straightforward. It's all the protocols directed towards the vSmart in order to bring up the control connection are standard. The actual propagation of the routing information to the vSmart and back to the far end edges is covered using OMP, or the Overlay Management Protocol. We'll discuss about that in brief later. The vBond is called our orchestrator because it's basically your call home server, which actually stitches everything together. So what you'll see a lot in Viptela and all the commands that you execute on the vBond would be tagged with this keyword orchestrator. The vManage is a separate beast, but more or less it's a standard application that's a web application that's running to manage your network. So there's not much to discuss there in terms of Viptela Cisco proprietary terminology. So let's look at a single vEdge, and we'll go from a bottom-up approach for the vEdge itself. We'll start at the TLOC, talk about the node, the site, and how it stitches into OMP. So that's going to be the general idea and the general movement for this lectures. So let's go on to what a TLOC is. So a TLOC, or a transport location, is just a unique identifier for a circuit that's plugged into an edge device. So it is this IP and a unique ID that identifies this endpoint on a particular vEdge. It's the termination point on a particular vEdge we call a transport location, or a TLOC. So like any unique ID, that you have a key and value pair for the TLOC. What are the keys for the TLOC itself? The key for the TLOC is 1, the IP address of the system it resides on. So the IP address of the vEdge itself, the system IP of the vEdge, is one of the keys.
So to clarify, Vinay, when you talk about the IP address of the system, is it the circuit IP address or an IP address from the provider, or is it something else?
No, it's a IP address on the box itself that is used. It's analogous to the way a host name would be used on a vEdge by the service provider to actually identify the box.
So could we consider it similar to a router ID?
It's like a router ID, yes. It is analogous to the router ID. So the IP address of the system. Second, you have a color, which I'll elaborate on further, and you have the encapsulation used by this TLOC to establish a tunnel to the far end vEdge. So this encap for us could be the IPsec or GRE, and we default to IPsec on all our boxes. So the unknown term, color. So why we need color, and how does color make a particular TLOC unique? So as you can see, you could have multiple circuits residing on the same vEdge. You could have AT&T and Verizon circuits on the same vEdge. These circuits cannot be uniquely identified by just the system IP and the encap. We had to introduce a third parameter to make this key unique, and that was color. Now, how do you use color? So the color is basically of two types: private and public.
So the color that we're using here is a means to describe the circuit types that we have.
Yes, that's true. So it creates a uniqueness for the interface itself that's connected to your transport or your circuit, and it also is overloaded in terms of the property of the circuit itself. So how we use color to identify the type of circuit is using two distinct types of colors. So we have private colors. These could be private 1, private 2, MPLS, and we have public colors, which are more or less all the colors you see in the spectrum itself: green, blue, gold. So anything that's an actual color is more or less a public color. We have a few more public colors called public internet. We have default, which is public. Now what they mean in each context is a private color has no NATing in play for connectivity. A public color has a NAT in play to provide connectivity. So consider this V edge having two circuits, and consider a NAT out here. So you have IP address A, port P. At this end of the V edge, you have A prime, P prime on the other end of the V edge. For this circuit, you have no NAT in play, so you have X and Y as the IP and the port, and that's it. There is no X prime, Y prime. So what the color actually signifies is I want to give a public color to this circuit, saying that, hey, this color, the TLOC color is blue, the TLOC color is MPLS. What this tells the far end V edge is, if I need to get to a TLOC whose color is public, I must use the NATed IP to actually establish a connection back into the V edge. Using the private IP is of no use because this NAT box is going to basically black hole your traffic, drop your traffic, and not let it through into the V edge itself. On the other hand, the private color signifies that, hey, the IP address and port number that I have provided to you is reachable privately, directly. There is no NAT in play. You can get to X, Y directly without having to worry about a translation that's happening in the middle.
So if we wanted to describe this, the color is a tag for our circuit, and the type of colors tell us if it's an MPLS style circuit or if it's an internet style circuit.
Exactly. So the color has significance in terms of the type of circuit. We leverage that in terms of how we want an overlay to actually come up, how it looks. So how we do that is, so let's now look at a couple of V edges sitting in two different sites. Let's say this is an MPLS circuit, and let's say this is an internet circuit. What we want to do here is essentially have connectivity from edge to edge over the MPLS circuit, that is using this TLOC 1, and have internet connectivity over TLOC 2 between the two edges. As you can see, there is no way for TLOC 1 to actually establish a connection to the far end TLOC that resides on the internet circuit. So we leverage color over there, where we are saying, hey, this is an MPLS circuit, this is a public internet circuit. Similarly, this is also identified by the same label, the same color, MPLS. This is also identified by the same color, public internet. And what we can now do is, either through policy or through knobs that we provide, restrict the connectivity between circuits depending on type. So we say, hey, using the keyword restrict, I want to just have connectivity between the MPLS and MPLS colors alone. I don't want to try to establish a connection between the MPLS circuit and an internet TLOC. I know for a fact that's not going to succeed. This is a completely private network. This is a public network. They don't have any translation table in the middle to actually allow for connectivity. I'll want to restrict this access. So I'm leveraging the color to actually shape my network, the way my overlay looks. Again, so The overlay is anything that resides on the WAN side, and so anything.
So if we go back to the original terminology, looking at what you've drawn, the color tells us the circuit and the type of circuit it is.
Yes.
And the encapsulation tells us if we're using IPsec or GRE.
Yes.
And the system IP, or which is akin to a router ID, tells us the uniqueness of the device.
Yes.
So how does that tell us what is a TLOC? Would it be fair to say that a TLOC represents a tunnel endpoint on a device?
Yes, the TLOC is the endpoint. It is an endpoint. It's a terminating point for any tunnel, be it an IPsec or GRE tunnel, on the Viptela SD-WAN overlay. So an endpoint is the TLOC, identified again by the system IP, the color, and the encapsulation. The color is overloaded. It's the use of the color that tells you whether it's a private circuit or a public circuit. Further digging deep into the color, we also overload it to let the provider tell us about their connectivity matrix, letting us know if the private and the public networks can talk to each other, and then shape their network according to that, you leveraging the color itself.
So Vinay, one quick question regarding your TLOC attributes, such as private IP, public IP, private port, public port, private port. The question is, when I say color and I say public gold, it'll prefer that, correct?
It'll treat the circuit that's connected to it to be a public circuit, and it'll assume that there is a NAT translation that's going to take place. So if you are actually physically connected to a private network, you want to actually configure a private color. You don't want to mix the two up. I'll tell you why, is because the V edges understand color. So the edge device, when establishing this IPsec tunnel, is going to use a particular IP address and port number to establish this connection based on the far end color. So if my color is private and the far end color is private, I use the private address itself, the private mapping. So it was AP. If I am private and the far end is public, I'm going to use the public mapping, A prime, P prime. And public to public is going to be A prime, P prime. So if this circuit was actually a public internet circuit, and you landed up giving it a private color, like private 1, you wouldn't be able to actually establish a connection, because you're telling the far end that there is no NAT in the network itself. I hope that answers that.
Yes, thank you.
Okay. So now that we have spoken about the TLOC, let's talk about the two sections. The TLOC, so each V edge or each edge device consists of two portions, the WAN segment and the LAN segment. All of the SD-WAN solution, all of Viptela proprietary or Cisco proprietary WAN resides on the WAN side, which is on a reserved VRF or VPN called VPN 0 or VRF 0. So all these terminologies that we have used so far all reside on the WAN. That is the internet-facing side of this system. The office-facing side of the system, the branch office-facing side of the system is LAN. This could be the engineering department, the sales department, so on and so forth, having their own subnets. Each of these segments can have their own routing capability and are segmented using VPNs or VRFs. So you could have VPN 1, VPN 2, each servicing a certain subnet, a certain routing domain for your office or your branch location itself. VPN 0 is our VPN. It's a reserved VPN that we are going to use to establish an overlay. Now,
so when we describe VPNs, these are similar to classical VRFs.
Yes.
These are separate layer 3 routing domains.
Yes.
With the exception being VPN 0 is a specialized VPN for the purposes of the WAN.
Yes. So VPN 0 is what we use for bringing up the WAN network to establish TLOC to TLOC connectivity. We let the user, our customers, define all the VPN segments they have within their network on the LAN segment of it, and then not worry about actually connectivity between the two LAN segments. So VPN 0 to VPN 0 connectivity is our problem. We have automated this whole section for you. The moment you define VPN 0 in your network, the remaining VPNs, your service-side VPNs, now are able to communicate with each other the moment the tunnels between the edges are brought up.
When we talk about VPNs and the equivalency of VRFs, in VRFs we also have a term such as route target, route distinguisher. Is that also consistent here?
So for us, it's a VPN label in order to decapsulate at the endpoint itself. For us, the overlay is actually managed. So I'll go on to actually OMP. That'll give us a better idea of how these routes are actually leaked across the edges. And we have something similar, but we use OMP to actually distribute these routes across the network.